Hello, welcome to another software short video. Today's topic is called What is Software Common Cause and How Common is it? And that's just what I'm going to go over. I'm going to use a few PowerPoint slides to go through a presentation. And that's what I'm going to go through. What is software common cause and why do we even care? And I'm going to go through and present the results of a study I was involved in that went through historical analysis to show how software has been failing. And so I'm going to show some statistics of how, when and how software has failed, why it's failed, where in the code it has failed. Surprisingly, there's very little information out there on this. So hopefully this is informative. Why do we care? Because especially for safety critical systems, and I'm going to sort of focus on aerospace, the software controls everything and it can be safety critical. So what this really is going to be a talk is about software and automation, how failures in general, how they have failed, and hopefully provide some lessons learned so we can design better systems in the future to guard against these things. Well, let's get to it. What is a software common cause, also known as common mode? They're the same thing, failure. In hardware, you can draw an analogy. In hardware, multiple copies of that hardware is usually used to provide some redundancy. And in aerospace, they call that strings. But in software, and this is the distinction, the same software usually runs on all of those computers or all of those strings. So in this case, any single software failure can result in a common cause failure. In other words, take down all the strings or do the same wrong thing on all the strings. And if only one processor is there, then you could say that any software failure is a common cause failure. So why care about this? It's because a single software load is a single point of failure, so it's zero fault tolerant. And if you have a safety critical system, lives depend on that one set of software doing the right thing. So if you have a common cause failure, you really have to, if you have any software failure, you really have to think about what is going to happen at this point or what can you do about it. Consider two cases on how software can fail. One way is failing silent, and we're all familiar with this. This is a crash, the blue screen of death, right? Everything stops. But the other case is erroneous output, and that means that the software or the automation, used synonymously, it's just doing the wrong thing. It's behaving unexpectedly. It's doing the wrong thing. So when you think about software common cause, you really have to think about both of these cases. And what if the software does something wrong? And what if the software stops? And why differentiate? Because the first one, the fail silent, is pretty easy to detect. But the second one is not. And the second one really requires maybe a human to watch what it's doing, maybe some kind of a software backup monitor. In the first one, you can just put a watchdog timer in and do something if it stops, reboot or tell somebody. But the second one is a little trickier to detect. Some examples of the fail silent case could be when the operating system halts due to memory access violations or arithmetic errors, underflow, overflow, or if the processor is being maybe there's a priority inversion, some processes are being starved. But the erroneous output case, I'm going to say is a broader case, and it turns out the vast majority of the manifestations for software errors are in this case, and I'll show you the statistics. But I've broken them down into 4 categories. Coding logic errors, and this includes the missing requirements, which turns out to be a large portion of software errors. When something is missing, some software should have been there, it's an unexpected situation that the software didn't know how to handle, or some just plain wrong code. Data parameter error is a lot of times software is being driven by data, especially more and more in modern software. So if there's a data parameter wrong, it'll cause the software to behave wrong. Unexpected inputs, you have sensor input coming in, you have user commands coming in. If those are unanticipated, it can cause the software to behave wrong. And then, yeah, either one of those are the inputs. So just to have some context, in space flight, the dynamic times of the flight are the riskiest times for something to happen wrong in the software. And this is during ascent, rendezvous, entry, re-entry, or even in the presence of delayed or loss of communication when the software is controlling things autonomously. So common mitigations during these times is to use backup software to maybe provide human in the loop control as well. But there's more options during the less dynamic times. If you have time to react, you can maybe put a new software load up there, you can reboot it, you can diagnose things. So your mitigations to the question, what happens if the software does something wrong, should be consider all this stuff in relation to time, in relation to the safety of the system. Before we get into the statistics, let's just quickly go through, sort of as a reminder, the existing NASA requirements for software fault tolerance. These are all from the human rating requirements for space systems. There's the requirement that systems have to have single failure tolerance to catastrophic events. So this would imply more than one copy of software most of the time. The second is to mitigate the hazardous behavior of critical software. I'm reading just the yellow, and have to have the crew ability to manually override automation. There's also a requirement in our software engineering requirement standard that no single software event should initiate a hazard. So these things drive the need for a consideration of what would happen if the software does something wrong or erroneously in critical situations, and frankly leads to the necessity of some sort of backup system. And now on to the fun stuff. So this is the result of a study that we performed at NASA in 2023 to study all the incidents in aerospace and some non-aerospace since the beginning of use of computers to characterize how software has failed. So this is 47 incidents. I just list them here. I'm not going to go through them. I do have a paper that's under consideration that goes through each of these in detail. I'll show that reference at the end. But for now, just take a look at this list and know where these statistics I'm going to show comes from. The first, just to get you familiar with the data set, most of these incidents are spacecraft, aircraft, launch vehicle. There's a very few commercial, 3 commercial and 3 medical. Otherwise, it's all either aerospace or DoD. And then the results of these are where the software behaved unexpectedly. 34% caused loss of mission, 15% resulted in loss of life, end of mission, close call. Some of them are a little less severe in delayed objective or loss of revenue or service. But just flying through the results, out of all these cases, 87% of them were erroneous and 13% were fail silent. So obviously, historically, erroneous is much more common. So the design should always consider erroneous as the more common thing that happens. And if there's something critical, you have to say, what is the risk if the software does something wrong at this point in time? And then if you look at where in the code it was from those categories that I went over, coding and logic was the majority of these. As I said, these include missing requirements, maybe insufficient modeling. So I have some fault-tolerant code tips here, but in making this short, I can let you read those. Data config accounted for 15%. And then if you look at inputs, command and sensor together, that's 23%. Now, another interesting thing here is the question is, if you use reboot to recover this, if you just try to reboot the computer, will it fix this? In the erroneous output case, the answer is no. 98% of these, only one out of 41 erroneous cases could have been recovered by a reboot. So reboot is really ineffective for recovering for this. And even in the fail silent cases, only half of the cases that fell silent were recoverable for reboot. So the takeaway is really rebooting is not effective if you have to rely on it. Certainly not for erroneous, and even questionable for the fail silent case. Absence of code. So these are the things that if you could have added code in hindsight, could it have prevented this mishap? And in 36% of those cases, the answer was yes. So that means that's interesting in that if you only test the code that's there, you're missing this 36%, and this includes missing requirements or unanticipated things. And finally, a more subjective figure is unknown unknowns, but it is something to consider. Our team, when we evaluated these incidents, we determined about 20% of these cases to be unknown unknowns with things you didn't know that you needed code for. So backup systems can be very useful to mitigate this unknown unknown phenomenon. I'm going to provide this is the study references for this. It's under consideration right now, but the title should be out there to search for in the future. So in conclusion, just a few bullets. Software common cause, common mode errors occur when a single fault, single error results in unexpected behavior, even if it runs on multiple strings. They can manifest in two ways, fail silent or erroneous. And a study of historical software incidents indicates that erroneous is much more prevalent. Rebooting is largely ineffective. Logic coding errors are the most common, then data config, and then 23% are input combined, sensor and command. Missing code was 36%, and unknown unknowns were roughly 20%. So the lesson learned here is software needs to be architected based on safety criticality and time to effect with these things in mind. So you need to consider erroneous much more than failing silent. Don't rely on reboot. Test like you fly. Use real hardware so that real sensor behavior and things like that are tested. And leave time for off-nominal testing, which will uncover some of these unanticipated situations. And finally, for the data config, parameters need to be validated before use and at each use. So even during operations, as parameters change, they need to be validated by folks. Oh, and also finally, the overall message here is consider using backup software and not having just this single point of failure. So that's it. I hope you found this video informative and useful. And again, please feel free to provide me comments or suggestions for more of these videos. Thanks and have a good day.